Okay, so same idea. No need to change what's working at this stage in the game, right? So again, we want to go through these steps. Again, I'll reiterate, this is a polynomial, and that means that our domain is the set of real numbers. Okay, you can always make that assumption if it's a polynomial. If it's not, you don't necessarily get to make that assumption. If we look at the leading term, that's x to the fifth, right? That's this front one. So it is odd and positive. That means we've got a John Travolta on our hands here. So now we want to look at our real zeros. Okay, and what that means is we're going to take our function h of x and we're going to set it equal to 0. So that's x to the fifth minus 6x to the third plus 9x is equal to 0. We can take out a factor of x, right? So x to the fourth minus 6x squared plus 9 is equal to 0. This is actually a perfect square trinomial. It's just maybe not as traditional of one. So I still have my x out here, but this is x squared minus 3. Okay, so this is a slightly unusual one because it is an x squared that's in here. So again, practice your factoring, but this is a perfect square trinomial we factored down. So again, we apply our zero product property that gives us x is equal to 0 or x squared minus 3 squared is equal to 0. X is equal to 0 is already done, right? It has multiplicity 1. So we know it's going to cross through that ordered pair. Here we can take the square root of both sides. Again, normally we need a plus or minus, but in this case, because it's 0, we just get x squared minus 3 is equal to 0. We get x squared is equal to 3, and we actually take a square root again. And in this case, we do need plus or minus. We end up with x is plus or minus the square root of 3. And this has, really, it's multiplicity 2 because the quantity was squared. So each of these, so I guess I can write out x is equal to the square root of 3 has multiplicity 2, and also x is negative square root 3 has multiplicity 2. What those multiplicities should really do for us is they should account for all of the degrees that we have, or all of the exponents. So we have a total of x to the fifth is our largest, so this is considered a degree 5 polynomial. So all of we should have 5 exponents accounted for. So it's 2 here, 2 more here, 4, giving us 1 more is 5. Okay. I think next we should do our y-intercept. So we've done 1, 2, 3. Y-intercept. This is where we find h of 0, right? So h of 0, we would say is 0 to the fifth minus 6 times 0 cubed plus 9 times 0, which is, it's just 0. And again, it kind of lines up with this point right here. So your y-intercept is just the origin. We've seen that a couple times. So if we lay out now our axes, I'm going to plot the points we've already got. So we already have 0, 0, right? Now, as far as the square root of 3, plus or minus square root 3, we are going to have to use an approximation. These are approximately, so square root 3 is approximately 1.7. You can add more decimals to it if you want, but you know, when we're drawing this by hand, there's not going to be a huge difference between 1.7 and 1.73 and 1.732. It's not going to look that different to us. So we've got 1, 2, 1 and 2. So 1.7 is partway through that, a little closer to 2. We're right about here. We've got a plus and minus. So we do need some more points to just kind of to help us figure this out, right? So let's plug in f of 2 or h of 2. So we're going to have 2 to the 5th minus 6 times 2 cubed plus 9 times 2. That's 32 minus 2 cubed is 8. So minus 48 plus 18. 32 and 18, those positives, if we add them together, we get 50. So 50 minus 48 is just 2. So we have an additional point. If we label 1, 2, we have an additional point right here, right? And that kind of agrees. I did positive 2, so I should plot it over here. So let's try negative 2. I went in the wrong direction. So that's negative 2 to the 5th minus 6 times negative 2 cubed and 9 times negative 2. So that's negative 32. This would be a negative 8, so plus 48 minus 18. So do you see that's the same thing with opposite sign? Negative 50 plus 48. This would be a negative 2. So let me explain what just happened. So I intended to plug in a negative 2 because I didn't put my signs here. So my brain said I was plugging in this number, even though I only wrote the number 2, and I went to plot it and I put it up here and I paused for a minute because I know that my end behavior says I'm up on this side and I'm down on this side. So this does not agree with the rest of my information. So I paused and I double checked my work, and that's when I realized, oh, I plugged in positive 2, not negative 2, and that's why I got a different answer. So that is part of why we go through these leading term tests, is so we kind of have a gauge of, am I even headed in the right direction? So this is actually the point at negative 2. And that actually agrees more with what we were expecting, right? Now, I'll also point out this value and this value, or these two zeros, both have even multiplicities. So we're going to be tangent at both of them. So my expectation is we're going to cut through here and change directions, as well as cut through here and kind of go back that way, right? So that's my expectation. I want to plug in some more points to kind of verify this. Bring my graph with me. So let's plug in some more points. Let's try a negative 1. So h of negative 1. We would have negative 1 to the 5th minus 6 times negative 1 cubed plus 9 times negative 1. Negative 1, this would also be negative 1. So plus 6 minus 9, that would be negative 10. Plus 6, that's negative 4. So we've got a point here, right? And that agrees with that tangent here. How about, we've already got 0, so we know we're coming back up to this point up here. And then I expect it to cut through here and come back down somehow. So let's plug in h of 1. So 1 to the 5th minus 6 times 1 cubed plus 9 times 1. I expect the same thing to happen as with 2 and negative 2. So we get 1 minus 6 plus 9, which is positive 10, minus 6, which is positive 4. So that gives us a pretty good outline of what this graph is going to look like. So again, we're coming from down here, crossing through these points. So again, a bit wobbly. It should have a little bit smoother. I think it's because of the size of it, but it should be a little smoother. Down, up, down, up. Something closer to that smoothness of it, right? But that's a pretty interesting looking graph. It's kind of a cool one. So almost done with this group. I will see you in the next one.